Finding characteristics of rational functions. Let's get into it. I always like to look and see what the horizontal asymptote is first, because when it's in standard form, it's way easier to see how the function's growing, right? We only care about the terms with the highest degree because they're growing the fastest, right? That 3x, that plus x, they're going to be left behind. That minus 20, once we're in the billions, who cares? So we only want to look at this 2x squared and that x squared. So 2x squared divided by x squared, those x's are going to cancel, so it looks like our horizontal asymptote is at y equals 2. It's important to note that the horizontal asymptote is a line, and it's obviously a horizontal line, so it's y equals. Make sure you write it as an equation. The vertical asymptote and the holes, we need to figure out those points of discontinuity, so where are we potentially dividing by 0? And to figure that out, we're going to have to factor. All right. Let's see. Multiplies to give me negative 20, adds to give me 1, x minus 4, x plus 5. All right, the top part here, what I would do is factor by grouping, draw the x. I already did it earlier. I'm not doing it again. For those of you who can factor quickly, I wish I was you. Anyway, hopefully I factored it right. I got 2x minus 4 times 2x plus 5. And then we can see that we got 2 points of discontinuity, one at 4 and one at negative 5. Which one's a vertical asymptote? Are there any holes? Well, since I can remove these, that makes them removable discontinuity, so that means we have a hole at x equals 4. All right, vertical asymptotes, that's the other option, right? If it's not a removable discontinuity, then it's definitely infinite. We're not going to have any jump discontinuities in a rational function. So our vertical asymptote is at x equals negative 5. Make sure you're writing that as a line. To figure out the x-intercepts, well, we need to figure out when we're on the x-axis. On the x-axis means that y equals 0. So looking at when y equals 0, well, the only way to make a rational function equal 0 is if the numerator equals 0. So we can isolate that numerator. X minus 4, set it equal to 0, use the zero product property, split it up. And that means x equals negative 5 over 2, and x equals 4. So negative 5 over 2, 0, and watch out. This is a big nope. Can x equal 4? No, it can't. We literally just said that if we were to plug in 4, we would be dividing by 0. That's bad. Don't you dare write down that x equals 4, right? 4 comma 0. Don't say that's an x-intercept, because it's not. We're not touching the x-axis there. We're jumping right over it. So this is a big nope. So only one x-intercept. Looking at the domain of this function, well, the domain comes from our points of discontinuity. So in this case, we got negative infinity all the way up until negative 5 is okay. But then I want to skip 5, right? Not include it, then keep going until 4, don't include it, and then keep going from 4 to infinity. Okay, pro tip, if you have 2 spots of discontinuity, then you need 2 union symbols when writing the domain. The y-intercept, I'm doing this a lot out of order, but it's how my brain works. The y-intercept is when x equals 0. So if x equals 0, well then that goes away, and that goes away, and that goes away, and that goes away. So we'd have negative 20 divided by negative 20. So it looks like our y-intercept is at 0, 1.